Under van der Waal interactions, the force at some distance r is given by the negative of 72 times u naught, which is the equilibrium potential energy, over r naught squared, which is the distance, equilibrium distance, squared, times some displacement x. And if you look at this and you consider that the distance, equilibrium distance, and the initial potential energy at equilibrium are constants, then this is just another form of Hooke's law, where you have a function equals some constant times x. So we can treat this as fr equals some negative kx, and say that k then is equal to 72 u naught over r naught squared. So this is 72 times 1.68 times 10 to the negative 21 joules over 3.82 times 10 to the negative 10 meters. And let's and now we can square, let's not forget to square the distance, and this will give us about 0.829 joule per meter squared. Keep in mind that a joule is a Newton meter. So we get this is the same as 0.829 Newton per meter, which is what we're used to for a spring constant, so they even have the same units. Now if we go to a table and find the atomic mass for argon, we find that argon has a mass that is given by 39.948 atomic units, and then we have to change this to kilograms by the conversion factor, that 1.66 times 10 to the negative 27th kilogram is 1 atomic unit. So the atomic mass of argon is 6.63 times 10 to the minus 26 kilograms. This will help us in the following way. If we're looking for the frequency, recall that the frequency is omega over 2 pi, and omega itself can be written as 1 over 2 pi times omega. Omega is the square root of k over m. So this is going to be 1 over 2 pi times the square root of k, which we found to be 0.829 Newton per meters, and then m, which is 6.63 times 10 to the 26 kilogram, and that gives us a frequency of about 5.63 times 10 to the 11th hertz.